Hello. This is a demonstration of the meaning of steady state in SFC models, which is similar to the concept of equilibrium as used in applied mathematics, but theoretically somewhat distinct from equilibrium as used by the rest of economics. This demonstration is using the SFC models package as seen here, and it builds and generates a model. This is model sim from Godley and Lavoie. The model itself isn't hugely of interest. The advantage is it's simple. If we look at the the output, it's being driven by this variable g, government demand. Government demand, it starts off at 20 and then it jumps to 30. This is basically a step response or two-step responses. And here, good, demand, good, or supply, this is the equivalent of output of the system, GDP. We start off here at 0, and then it jumps quickly and then converges towards a level, and then when G changes and jumps, then it moves towards a new level. These constant levels are what we call steady states. As you see, the steady state changes when G changes. And if we look, all the variables are either constant to begin with or converging towards constant value. This is an example. This is a parameter. It's a constant, so it's always constant. And so this, would meet the definition of an equilibrium using dynamical systems theory, but once again, not necessarily economics. So I tend to accidentally used equilibrium instead of steady state in my code, and I switched that to steady state. One of the things you see here is you're starting off at 0, and then suddenly you're converging to this value. Quite often we want to just see what happens when you change a policy, and you don't want to start from 0. So what we can do is we go quit, and what we say is, well, we're going to solve for the initial steady state, and then we'll run the model again, and we view in the chart plotter. The chart plotter, once again, it's not yet released on SFC models. Its source code is available at GitHub, but not in a different package. And what we see here now is we're starting at an initial steady state, and so we only see this one convergence. So, and how it did that, it basically had to set variables, so we start off, there's no movement initially. What we see here is we can change their source for the data, and what it did is, if you look at the k, the time axis, it starts off minus 200, goes to 0. What it did is it started off at negative time, and then it just checks, do all the variables converge towards a constant value? And if they did, you say, okay, that's that's your initial steady state, and then you apply those values for when we go into forward time. And so then we do here, you see it's the same. So it allows you to, the system settles down, and then you can say, okay, now we're going to play with variables and then see how they affect the system. And that's a nice feature from a developer point of view, because it's difficult. I mean, it's relatively easy to get model sim to settle down. You actually only have to change one variable, two variables if you want to keep your counting proper. But later on, it gets quite complex, and you might have to set 10 variables, and it's pretty hard to do that. This way, it just solves it for you if it can be done. There's no guarantee that there's an initial steady state. That's basically it. I mean, the only thing that we could change is we could define the notion of a steady state as a constant growth rate, and then the steady state would be ratios of variables that go at the same growth rate tend towards a constant. But that's a bit more complicated because not all variables have the same growth rates, even when you're in sort of a notion of steady state. Nominal variables grow at one rate, real at another. But we can formally define a steady state to handle that, and you just have to accept that there's going to be multiple growth rates. But within certain classes of variables, their ratios are constant. And for the solver, the initial steady state will eventually implement that ability. So it'll be definitely a lot easier to work with models that start off growing and not just at constant values. Anyways, that's it for this demonstration.